Hello, my name is Masar Sheikh, and this is Lab 2. So the purpose of this lab is to observe the projectile motion of an object, and in my case, it would be a balled up piece of paper. And through the tracker software, we would compare it to two computational models, one with the only force being gravity of the projectile, and then with the other model being a force of gravity as well as drag force, which can be calculated with the equation F drag equals to negative b v squared v hat, where b is the drag coefficient that we need to find in the experiment, v is the magnitude of the velocity, and v hat is the unit vector. The computational model of the experiment with the drag force of 0 displayed goes through the x-axis, uh, giving us unrealistic results, but the model with the drag force um, was found to have a drag coefficient of 0.0213 because it made the conceptual model the most accurate in comparison to the experimental data. So in the slide, we see the tracker software, and on the very right, we see a screenshot of the experimental setup with the origin that was placed right below the paper ball, the unit, the calibration stick that was calibrated to the meter stick, and you see the footprints in the red of the ball. And to the left of that, we see the graph with the top being the position versus time in the x direction being linear for the most part, showing that we had consistent velocity. And below that, we have position versus time in the y direction, which gave us a kind of bell curve shape. And below that, we have the data that we can use for Excel. For the computational model on the code, we set the ball M mass to 0.005 kg, which was the mass of the paper. We were able to initialize the position vector with the initial position from tracker as well as the initial velocity from tracker. We set up the time step of 0.067 and we set the value for gravity 9.8, and for the value of b, we set it equal to 0 for the one with no drag force, and we plug that into the equation of F net, which equals the vector of gravity times the ball's mass, which is the force of gravity, subtracted by the uh, to the F of drag equation. And for this experiment, we set the drag force to 0.0213, and on the bottom we see the model generated. So from the results, we see the scatter plot of all three data points. The one going all the way to the bottom was with no drag. The one in the yellow was the experimental model, and the one close to that in the dark blue is with drag force. And we see that because the one with no drag ran through the x-axis, and in our experiment that would be the table, it's unrealistic as um, that's not what the conceptual model followed. But after calibrating the drag coefficient, we found that a value of 0.0213 best fit the experimental model, and then we were able to get the vector for f of drag. And for the additional questions, what does this mean? After observing both conceptual models graphs, we see that the velocity versus time does not predict a terminal velocity, as it has no sign of plateauing. And an experimental model that could be done to find terminal velocity would be a free-falling parachutist, as he would increase in speed until the drag force acting against the force of gravity will be equivalent, giving him an F net of 0. And what if the ball was thrown at the same speed but directly upward, it would fall at the same rate as the force of gravity only acts in the y direction.